right, so example 4 seems like it'll finally give us some three-dimension action, but it's actually a little bit misleading. So we have an object attached to a parachute that falls at a rate of 15 feet per second in still air. If a 6-mile-per-hour crosswind blows horizontally from east to west, find the velocity vector that describes the situation as well as the direction and speed of the object. Well, there's a sign right there, because you can't find direction if there's 3 dimensions, because there's really not in this case. It's just that instead of dealing with the XY axis that we're used to, right, the XY axis has north, south, east, west. We have east and west because this is the x-axis, right? But we're dealing with up and down. So that's the z-axis. So we're actually in the xz plane, not the xy plane. Right? Okay, and then this is west. Okay, so we have an object that's falling. It's falling down. So we have a rate of 15 feet per second. Now, here's the trick. I don't know if you caught it, but my eagle eyes spotted that those two are different. So that's a problem for us because we can't have them, when we finally do the work, we can't have it be that they're different. So we know that the rate is 0, 0, negative 15. So if we want to do it in the xz plane, so the velocity of the falling parachute, I'll do F for falling, is 0 in the east-west direction, negative 15, and that's feet per second. Okay, and that would be straight down like this, right? That'd be 15. That's the velocity of the falling parachute. I did F for falling. You could do P for parachute. That would work too. Okay, so now we have a wind blowing horizontally from east to west, right? And it's a 6-mile-per-hour wind. So it's that. That's the velocity due to the wind. And it's going that direction. Now we know the velocity due to the wind is negative 6, 0, but that's miles per hour. And that's no good to us. Miles per hour, actually let me write out miles and hours just to remind you guys how to do unit conversion here. That's miles per hour. So we have to either convert this one to miles per hour, this one to feet per second. I mean, it's kind of whichever, but I'm going to convert this one to feet per second. So I'm going to get rid of the miles. So for every 1 mile, there's 5,280 feet. And then for every 1 hour, there's 60 seconds in a minute and 60 minutes in an hour. So that's 3,600 seconds. Okay, so let's go find that number with Desmos. All right, so I'm going to insert an expression right here. And I want to take 6 times 5,280 and divide it by 3,600. And we get 8.8. So this is 8.8, 0. And it'd be negative, of course, sorry. I got room for my negative. And that would be feet per second. Again, we could have gone the other way and reversed this one. It doesn't really make any difference. We just have to keep them the same. Okay, so then the component, right, the velocity vector that results, respect to the ground, if you will, is equal to the velocity from the parachute falling plus the velocity of the wind. Okay. So this would be equal to negative 8.8. I can write it over here. Negative 8.8, comma, negative 15 feet per second. The 8.8 is because it's going west, and the 15 is because it's falling. So this is a pretty straightforward one. All right, so there is our velocity vector. The speed of the object is relatively easy to find. Speed would just be the magnitude of the velocity, which would be the square root of 8.8 squared plus 15 squared, because of course we could just turn them both positive. That would work. They were going to be positive anyway when we did it. So we're going to take the square root of 8.8 squared plus the square root of, well, plus 15 squared. It has to be under 1 square root. And we get 17.39. So it's 17.39 feet per second. That's the speed of the object. So it has its falling velocity, and then it has an added component of the wind pushing it around as well, which makes it go even faster as a component piece. Okay, now what about direction? Well, the direction is going to be a little strange, but let's start with it. The tangent of theta is the v2 divided by v1, which would be the negative 15 over the negative 8.8. Right? And we can see that if we push these two together, right? If you imagine the wind going this way, you can see, hopefully, that you're going to end up down here, right? Negative 8.8, negative 15. So you're going to end up in that direction. So we can see we're in quadrant 3. So the reference angle is the arctangent of negative 15 over negative 8.8, but that's not going to be the angle. It's just going to help us get to the angle. All right, so I'm going to take the arctangent of negative 15 divided by negative 8.8, and we get 59.6 degrees. Okay, 59.6 degrees is over here. It's on this side. This is 59.6 degrees. And so you can see, because of geometry class, that that means this angle here, right, is 59.6 degrees. Okay, but that would be 59.6 degrees south of due, well, not south, below due west, right? It's falling 59.6 degrees. Below that western. So instead of falling straight down, it's getting pushed along by the wind, and so it's falling at an angle. So the object is, so if I want direction, here, let me put it this way, direction. It's a little strange because it's not really like south. So it's 59.6 degrees below or downward from due west. So it's getting pushed off course in the westerly direction. And that's, of course, because this is the xz plane, not the xy plane. So that's why it's below and down. All right, so now what about this one? Well, this one's actually going to kick it into gear and get some third dimensions in here. So we have a model airplane is flying east at 10 miles per hour relative to the air and encounters a horizontal crosswind blowing northeast at 5 miles per hour and an updraft of 3 miles per hour. Find the velocity vector and speed relative to the ground. Now notice, it didn't ask for direction. That's because this is three-dimensional. You can't do it with 3 dimensions. We kind of snuck it in over here because this was really 2 dimensions, right? But we're going to not be able to do direction here. Okay, so let's see here. We have our standard north, east, and then up is right here, right? So this is up. So this is the positive y-axis, this is the positive x-axis, and this is the positive z-axis. Okay, so we have the model airplane flying east at 10 miles per hour relative to the air. Oh, excuse me, flying east. Okay, so that means that it's flying east at 10 miles per hour relative to the air. It's coming out at us. It's flying east at 10 miles per hour. So that's the velocity of the plane. So the velocity of the plane is 10, 0, 0, right? Because it's direct east. That was pretty easy. And the updraft is also pretty easy. So the updraft is 3 miles per hour. So that's a lift right here of 3 miles per hour. So that's the velocity of the updraft, if you will. So 0, 0, 3. And these are all miles per hour. I'm not worried about it the way I was the previous problem where there were different units. Okay, now the most complicated part is the velocity with respect to the wind. So the velocity with respect to the wind is given to us without you realizing it. So we have a velocity with respect to the wind. It's blowing northeast, so that's this direction. So that's northeast. It's got a 45-degree angle here, or 45-degree angle here, whichever way you want to think of it. Usually we think of it that way from the east, so we'll do it that way. Okay, so the velocity with respect to the wind, and the magnitude of that is way bigger than it should be. So hold on. Let me just make the pink one longer, because that one's supposed to be magnitude of 10. So let me kind of shoot this one out. So that's a magnitude of 10 now. So that's the velocity with respect to the wind. And then I'm going to shorten this one, because it's only supposed to be 5. So it's not supposed to be nearly as big as I'm drawing it. So let me make it just, I'm going to exaggerate just a little bit. There, it's 5. Right, that's the velocity due to the wind. Okay, so that is 5 cosine of, and then the angle is 45 because it's due northeast. So 45 degrees, and that's the positive east north. That's quadrant 1, octant 1. Everything's fine. So 5 sine of 45. Now, if you look at the other components, they all have x, y, and z. This is in the xy plane, so the z component is 0. And there we have it. All right, now the velocity due to the relative to the ground, relative to the shore, I can talk, is the sum of these components, right? It's the velocity of the plane plus the velocity of the wind plus the velocity of the updraft. Those three pieces combine together to make the combined velocity of this model airplane. Okay, so let's see if I can write that in real small. So the velocity is 0, 10, 0, 0 plus 5. Well, okay, the cosine of 45 degrees is the square root of 2 over 2. So this is 5 square root 2 over 2, 5 square root 2 over 2, comma 0. We actually know what that is. I can write it over here. So this is 5 square root 2 over 2, 5 square root 2 over 2, comma 0. Right? Because it's a known angle. I don't even have to go to Desmos and figure it out. And then this is 0, 0, 3. There we have it. Okay, so I do need to go to Desmos to add. The one piece I can add is the z components, 0 plus 0 plus 3. So I know that my z component is going to be some number 3. Like, I know that. That's going to happen. And this will be in miles per hour. I know that. So let's go find those numbers. So I need 5 square root of 2 over 2, and I need 10 plus 5 square root of 2 over 2. And then I need 10 plus that. All right, so I get 3.54, 3.536, and 13.536. So let me write those down. So 13.536 and 3.536. And there we have our velocity with respect to the ground. Lovely. Now we don't need direction, right? Because we can't. We know the direction on the compass headings, and then we know the uplift, right? But together they're going to combine to make this, there's a vector kind of pointing out into space that you can't deal with. So, but you can find the speed. Speed is the magnitude of that velocity. So that'd be the square root of 13.536 squared plus 3.536 squared plus 3 squared. That's a squared there. It looks like a 2. Okay. Oop. I just don't like it. So I've got to fix it. 536 squared. There we go. All right, so let's go to Desmos and find that value, and then we'll be done. So the square root of 13.536 squared. And again, if you want to, you could put this in with parentheses. That'll keep it the accuracy nice and high until the very end. Because I'm a mathematician, that's the kind of thing I do. All the science teachers don't like it because, of course, we don't have significant figures, etc., etc. But that's just how I am. There we go. So we get 14.3 miles per hour. And we found the velocity, and we found the speed. And we cannot find the directions, so we're all done.